job because there are so many things to say about the contributions of Vinod in cryptography in general. So I'll restrict myself to lattices. And I just mentioned lots of foundational works on computing on homomorphic computing on data, and also IB, attribute-based encryption, predicate encryption, function encryption. Go ahead.
Okay, you got it. Good to get the green light. Well, thanks, Damien. Thanks to myself for inviting myself to get stuff. All right, so the talk will really be on fully homomorphic encryption from lattices. I have this, what Damien pointed out is a non-committing title. From this, I could be talking about one of several different things, but really I'll be talking about fully homomorphic encryption. And the rest of the day will be some other kinds of things you can do from lattices. So let's just get started. What are lattices and LWE good for? What I really should be asking, what are lattices and LWE not good for? And the slide would have been a little bit shorter. One thing that they're good for, as you saw from perhaps from Chris's talk, is to construct all kinds of sort of good old crypto. Things that we knew how to do from other assumptions, factoring or discrete logs or elliptic curve discrete log or whatever. We can sort of recreate most of these things from the hardness of LWE. That includes public key encryption, which you saw already, oblivious transfer, which you didn't see, but and you probably won't see today, but you can do it. Chosen ciphertext secure encryption, identity-based encryption, which you did see, hierarchical IB, which you did not see. And really, this list keeps going on and on. The most recent kind of kid on the block is non-interactive zero-knowledge proof for NP from the hardness of LWE. I have a very special relationship with this problem because 4 years ago, it was at the Simon's program that I actually put a bounty on this problem, and I lost. So I'm not gonna make that mistake again. So this list keeps going on and on, really, and lattices seem LWE in particular seems very versatile to build crypto systems. And then we can also do crazy crypto, by which I mean sort of achieving notions that we did not know, that we still do not know how to achieve from any other assumption. Fully homomorphic encryption is perhaps the signature example of one such application. The only way we know to build fully homomorphic encryption of any reasonable kind is from LWE, through better OS. This list keeps going on and on. Fully homomorphic signatures, constraints to random functions, which you will see at the end of the day. Attribute-based encryption, which Shweta will tell you about. Trader tracing, lockable obfuscation. I can keep going on and on. It's not that you should sort of know all these buzzwords, but really you can do a ton of things. And at this point, it seems as if potentially you could do all of cryptography. You could base all of cryptography on the hardness of LWE. We're not there yet, and that's intimately tied to the question of building sort of program obfuscation or indistinguishability obfuscation. So there are still frontiers to be explored for a grand unification of cryptography. Very good. So today is Crazy Crypto Day, and I'll begin with fully homomorphic encryption. Okay, so what is fully homomorphic encryption? How many of you haven't seen a definition of fully homomorphic encryption here? Let's just calibrate myself. Have not. That would be easier. I don't want all of you to, yeah, right. Oh, fun. Okay, good. Okay, so I'm not just kind of, doing the right thing. All right, good. So imagine two parties. Okay, there's an Alice who has an input X, and she wants to get it computed, a complicated function on it. She wants someone else to do it, the cloud, but she doesn't want to reveal X to the cloud. So what does she do? She encrypts X, sends it to the cloud. And what you want the cloud to do is to take the encryption of X and somehow do magic resulting in the encryption of f of X without actually knowing what X is. That's the homomorphic part of the implementation. Okay, this is what you do. And once that's done, the cloud doesn't know anything. The input, the intermediate sort of values in the computation. So the computation, I'll think about it as a function or really concretely as a Boolean circuit, arithmetic circuit, doesn't know anything. Doesn't know the result, doesn't know the input, nothing. Once it's done, the cloud sends it back to Alice, who has the key. She can decode and find the result. Classical, fully homomorphic encryption. What do we need? We need correctness, of course. That we need this commutative diagram that you encrypt, you homomorphically evaluate, you decrypt. You should get the same result as actually computing the function F in the clear. Yeah, that's correctness. Yeah, encrypt. Eval is something that takes a ciphertext, or in general, many ciphertexts. A function computes together, and once you decrypt, you get it. This is the obvious one, right? And security is what is security? Security. Really, most commonly we think about security for Alice. Okay, that is, whatever she sends out of her system should hide her input completely, semantically, or in an NCPA sense. Rather, the encryption of X, or rather a sequence of encryptions of X, should look like junk, should look like maybe encryptions of 0 if you will. Right? That's what you want. So it's the classical notion of CPA security, no change at all. Then there's a notion of efficiency, which is really what sort of homomorphic computation is about, which says that this ciphertext really should look like an encryption of the result f of x. You shouldn't do sort of complicated things like blow up the size of this ciphertext proportional to the computation time or the circuit size. This guy really should look like the old encryption of f of x. Right? Way to formalize it is that the length of the ciphertext, the description length of the ciphertext, the number of bits that the cloud sends back to Alice, should be independent of the circuit size of f. This really should be really independent or polylogarithmic if you want on the circuit size. Okay, makes sense so far? You're on the same page? Good. You could ask for more. Poor cloud, why he feels left out, okay? So he says, look, I might want to hide the function I'm computing from Alice. Why not? Okay, that makes sense. To that end, so Alice does know something about the function. She learns x comma f of x. She learns one input-output pair. Yeah, and I want to say that that's it. Really, you don't learn anything else. In other words, that C prime reveals no more than f of x to Alice, and Alice actually knows the private key, so she can actually decrypt, learn f of x clearly. Maybe more, I want to say no more. That's it. That's all you can do. That's called function privacy in the literature. Good, so these are the two properties. Three properties, four properties. Correctness, security, compactness, and function privacy. Okay, and fully here means that this encryption system should be powerful enough to evaluate any circuit, any polynomial size circuit on encrypted. Good so far? All right, so let me start with two theorems that make our lives vastly simpler. Not vastly, but simpler, yeah? The first theorem says that function privacy, don't worry about it. Okay? So the theorem with Craig and Shai shows that you can turn any homomorphic encryption scheme generically without any assumptions, any additional assumptions, into one which is also function private. Okay? So really the hard thing is to hide the input and compute on it. Hiding the function sort of comes for free.
Depends what you mean by free.
Polynomial. We are in asymptotic land here. I'm not going to yesterday. Forget it. Okay. Asymptotic. Yeah.
You're assuming Alice honest but curious.
I am going to assume that both Alice and the cloud are honest but curious. You can take care of it by external means, but not today. Very good, thank you. Good questions. Yeah, but this is a theorem, right? It's not a you can analyze the polynomial blow up or whatever, but really, as a theorem, it says you need to make no additional assumptions for the polynomial constant. Okay, that's fine. That's what free is. Theorem 2 says you could define a secret key version of homomorphic encryption or a public key version. Yeah, so just like you could define a secret key version of encryption and a public key version of encryption. And a beautiful theorem of von Rothblum says that you can go from any secret key homomorphic encryption, even additively homomorphic encryption, to a public key homomorphic encryption. We don't know how to go from a secret key encryption to a public key encryption. That would be major. But if you have a homomorphic secret key encryption, you can generically, completely generically, and actually quite efficiently convert it to a public key homomorphic encryption. One could, in retrospect, think of all the public key homomorphic encryption schemes as doing precisely this. Okay, all right. So these theorems actually make our life simpler because I don't want to care about public key. I don't want to care about function privacy. I'll, work with the other things.
What do you mean when you say even additive? So you're saying that
additively homomorphic private key encryption.
converts to any homomorphic?
Additively homomorphic public key encryption. So the homomorphism, whatever you had, you more or less preserve. You lose a little bit, but you more or less preserve. Yeah. Okay, so this is what that is. There's a history lesson. I don't want to do too much of it. I did spend quite a bit of time sort of preparing the slide. So yeah, so the notion was defined by back in the 70s, right after RSA, by Rebecca Stedman and Lattices. First homomorphic encryption scheme in some sense, which is CPA secure. But think about it as it's Goldwasser-Micali. Right? It was the first CPA secure encryption scheme. Turned out to be homomorphic as well. So there you go. And then Diffie-Hellman, they did multiplicative. I mean, you can think about Diffie-Hellman the way we typically think about it as a multiplicatively homomorphic encryption scheme over the subgroup of quadratic residues, if you will. Lots of other sort of additive or multiplicative schemes over different groups. Then the only kind of, sort of progress that we made in, I don't know what it was, 25 or so years, was this work of Bonnet, Go, and Nissim, where they showed how to do arbitrarily many additions, homomorphic additions, and one multiplication. So that's what we call one multiplication. You might think, why one multiplication? I'll let you figure it out, but that's what you can do. Okay? And if I can do one, why can't I do two? There's the reason. Okay. All right, that's where we stood. And then tons of more works which you could call homomorphic encryption. They don't look like homomorphic encryption. You can call them homomorphic encryption. That's what it is. Really the first breakthrough, yeah. They don't look like, Goldwasser-Micali, right? The ciphertext is a group element. And then another ciphertext, another group element. You multiply group elements and then you get another group element. It's a natural kind of homomorphic encryption. But you could think about more complicated things that have the same properties, which is compactness and function privacy, which don't look like group elements. It could be something more like garbled circuits, for example. Right? So Craig came up with the first candidate fully homomorphic encryption scheme for real. Yeah, that was fantastic. It marked a huge change for those of us who were around that field, and actually to some few kids as well. Okay, and several people built on top of it. The scheme was actually based on a very strong set of assumptions, some of which, or at least one of which, is known to be in quantum polynomial time at this point, according to Leo, right? But anyway, so built on a set of assumptions, wasn't particularly efficient, but it was the first solution. Okay, so it's a landmark change from what existed before. And then a couple of years, Vika and I came up with the first LWE-based FHE scheme, and that's what I'll start telling you about. Built on top of it with a couple of other works, maybe more. So in the field we refer to these as the first, second, third, maybe the fourth generation of fully homomorphic encryption. It's not clear what these things actually mean, but among friends we give these names. I haven't gotten there yet. Good. This is the third. So Craig, Gentry, Sahai, and Waters came up with yet another LWE-based FHE scheme. So you can say, well, what's good about it? It's in fact actually less efficient than the 2011 scheme. So like, what is going on? But it's beautiful. It's as you will see. In fact, you'll keep seeing it throughout the day because essentially everything you see today is built on top of GSW. Okay, and that again was built on by several people. Leo and Daniele had a work on it, right? Building on it, and Ilaria, I see some. Yeah, okay. Several works that built on top of it. Fourth generation, well, I don't think this is my terminology. I haven't really consulted with any other experts, is a work of Jung-hee and others who came up with an approximate FHE scheme. Not going to say what that is, but okay. That's your answer.
What way is it better?
What way is it better? It solves problems in practice that I wouldn't solve with BGP. Or
So it's more efficient.
it's
for
more
practice.
efficient. It's more efficient. It's nicer in a different sense than GSW. You know what I mean? Actually, you don't know what I mean, but but doesn't matter. But it doesn't matter. It's a different scheme. You look at you know it's sort of like look at this scheme. You'll know. So what I'm going to do is I'm going to go for BV. And I realized that I had, the last time I gave a talk about BV was in San Diego. So Daniela, it's not correct that I didn't ever give a talk about it. I did talk about it in San Diego in 2010, actually. So 10 years has passed. Hopefully I remember what the scheme is. And GSW, if I get to it. And finally, I want to say, so here's a thing about history, right? So, these schemes, that old world schemes, most of it is obsolete, but there are very nice ideas that persist from these works. In particular, Craig's work came up with the idea of bootstrapping a homomorphic encryption scheme, which we will get to in a and that really is the only way we know to get a real fully homomorphic encryption scheme, one that can evaluate arbitrary circuits without any, stars on it. Yeah, very, very nice idea. It persists to this day. Major open question whether you can actually get rid of that one sort of persisting contribution from the original FHE scheme. And then again, Smart and Berkouteren came up with this idea of sort of packing many ciphertexts into packing many plaintexts into one ciphertext and computing on it together, what is now called the SIMD mode of evaluation, which is again fantastic. It has persisted to this day, and people have built on it. And really, the reason why FHE is even thought of as being remotely practical at this point owes a lot to so these works have their value, and it's worth actually going back.
Is as old as 2009?
Yes. Actually, Nigel and Frey took Craig's scheme, simplified it, and they also showed how to actually do. And then sort of we built on it in BGV, and then Gentry, Halevi, and Smart, and so on and so forth. But it's originated from there, as far as I know. Okay, so that's what we're going to do. Yeah. So 1, 2, and 3, and you'll probably only get to 1, but. Yeah. Okay, so let's start with the Big Bang, which is Regev. In fact, even before Regev, there is Proto-Regev, okay, which is the following scheme. To encrypt a message M with, what is that second parameter? It's the noise rate. It sort of measures how big or small the noise is. Here's what I do, and you have seen this already. You pick a random vector A, zq to the n. The secret key, you think about it as an integer vector, z to the n. You add a noise, which is bounded, add the message to it. I think of the message as an element in z mod qz at this point. Okay, so it's proto-Regev. Good to go? Okay. All right. Oded is not here, so I take the liberty to, he'll watch it later probably. That's what proto-Regev looks like.
He's watching this live.
Say again?
He's watching the stream.
Live. But you see, I can talk to him. He can't talk back to me, so it gives me a distinct advantage. All right. So here's a syntactic change. I don't want to think about sort of A comma B in the ciphertext. I really want to think about the ciphertext as one vector in one dimension higher, such that the inner product of this vector with the secret key, which is again the old secret key concatenated with 1 or -1, is in fact the error plus message. I didn't do anything. It's just a syntactic change. Makes my life easier. Okay, yeah, that's good. All right, if I can encrypt numbers, I can encrypt vectors. Just encrypt them separately. Okay, so again, there the ciphertext would be a matrix instead of a vector, whose product with the secret key is an error vector plus the message. Yeah, so it's nothing, yeah, all obvious. Yes, obvious. Okay. All right, so good thing about it is all these things that I showed before are additively homomorphic. You take two ciphertexts, add them together, you know, it is an encryption of the sum of the messages, many messages, if you will. You would have noticed already that when I add two ciphertexts, the error increases. This is a curse that's going to be with us for life, for the life of this talk, and for the life of lattice-based cryptography, but you live with it, okay? So when the error grows to double what it was before, it's not a big deal. You can handle it. All right. What I would like is, what is next after addition? Scalar multiplication, potentially, right? I'd like to take a ciphertext, encryption of M, and I'd like to compute an encryption of some scalar alpha times the message. That's okay. It makes perfect sense. And that doesn't work. At least, right away, it doesn't work. Why? The obvious thing I would do is I would take the ciphertext, multiply it with the scalar. What I would do is it would multiply the message with the scalar, it would also multiply the noise with the scalar. And really, I want to think about the scalar as an arbitrary number in Z mod QZ, so it increases the noise by a great deal. You know, the noise could really be an arbitrary number or vector in Z mod QZ. Yeah, that's not good. That's not good, yeah? Okay, so we want to actually solve it. And here is the first variant of proto-regget. Really, this is proto-regget for me. Second try. Here, when I want to encrypt a message M, I don't sort of encrypt M. Rather, I encrypt M tensor with G, which is a fancy way of saying, look at the big vector whose coordinates, whose concatenation of M, 2M, 4M, all powers of 2 times the message. Okay, so it's a vector that is roughly log Q factor longer than M itself. Encrypt that. Okay, so that's what I'm going to do. Now I claim that suddenly this actually supports scalar multiplication. Okay, so the one thing to notice is that even the old scheme, if I multiplied it, if the scalars I used were small, let's say 0 or 1, it's good because the noise grows by, I don't know, 0 or times 1, which is great, right? So that's good. It was somewhat scalar multipliable. This one is fully scalar multipliable. And how do you do it? It's the oldest trick in computer science, think of bits. Okay. In other words, take the ciphertext, take the plain text, sorry, alpha, break it up into bits, right? So now you have an encryption of, so I have alpha, break it up into bits, so sum alpha I 2 to the I, these are bits. What I want to compute is alpha times M, so of course I can write this. And associativity is a beautiful thing, so you do 2 to the I times M, yeah? So now you have alpha I that are bits, you have encryptions of 2 to the I times M. You do scalar multiplication, except with small constants. Beautiful, yes? This is such a, I don't know, we were actually, I think we did it for the first time in BV, but I'm so embarrassed we were so embarrassed to say, oh, we invented bit decomposition. It doesn't make any sense. But, you know, it gives us such huge mileage in, lattice cryptography. In fact, you can trace its origin in lattice cryptography to a work of Itai 99, where he came up with trapdoors. This is, you can trace its origin in humanity to the notion of bits.
You can even take it back to the knapsack crypto system and the super increasing sequences.
Is that right? But yeah, maybe. Yeah. You see, we can go back to Dirichlet house. Yeah. So very simple trick. Lets you do scalar multiplications by arbitrary scalars, and this will keep showing up. This sort of notion of bit decomposition. All right. So now you can actually do scalar multiplication. The noise increases from eta, which was what it was there before. To eta times log q. Why log q? Because you're adding up log q many ciphertexts. The number of bits in a number is log q bits. You're adding up many of those many things. So the noise increases by a factor of log q. Of course, if I can do scalar multiplications, I can do inner products as well. right? It's just scalar multiplications and additions. Yeah, so that this I can do as well. Okay, very good. So homomorphic addition, homomorphic scalar multiplication. We're making 2/3 of the way through. Yeah.
So when you take this tensor G,
Yes.
like encode like many copies of M different.
Yes, yes. So this is what it is. Yeah. So that M tensor G, I think about it as a vector with M, 2M, 4M, and so forth. Yeah, that's exactly. All right. So all that's left is homomorphic multiplication. Yeah. Well, that's really the heavyweight thing. To do that, let's actually go back to let's forget the proto and let's relieve that of the picture. And let's go back to what we know as the Raghib encryption scheme, which is E sub s. Yeah, you could really think. So, what is the problem with proto E of the message? You know, it wasn't the message couldn't be completely recovered. What you could recover is the message plus the error, which is not the entire message. Yeah. So this is, you should think about it as an error-corrected version of proto Raghib. In fact, actually, what we built proto Raghib prime is also an error-corrected version the original scheme, but this is a simpler variant. Yeah, so what I do is instead of putting an M here, I put an error-corrected version of M, which is M times Q over 2. Only difference. Only difference. Now, when you decrypt, what you recover is E plus MQ over 2, and you can read out the most significant bit. Yeah? That's good. All right. Good. Okay, so morphic addition is great. Decryption is great, right? I'm going to burden you with one more sort of variant of Raghib. Okay, all this is building towards the grand finale of homomorphic multiplication, trust me. Yeah, this is, you know, another thing that we notice, such a really elementary observation, that in LWE, Q doesn't matter. What matters is the ratio of the noise to the modulus. Q is sort of extraneous. One way to kind of formulate it is by saying, look, you know, I can think about the LWE ciphertext C as living not with reference to any particular modulus, but over the torus. Divide the whole ciphertext by Q. What you get is the ciphertext that lives in the torus times the secret key, which is an integer vector, which is error. Error also gets slashed by Q. And what you get is, I really shouldn't have a Q here. It should be ML. Okay, and really these two schemes are, you can go, these two ciphertexts you can go back and forth, you know, multiply or divide by Q. One thing I do want to point out is that this ciphertext doesn't live completely in the torus, arbitrarily in the torus. It's actually multiples of 1 over Q. And this will come up later, but yeah. So we came up with like 4 schemes, just to wrap, yeah. To summarize. Proto Raghib, which didn't even have decryption correctness. We modified it in 2 ways. One is to allow for scalar multiplication. Addition always is the case, always true. Also got scalar multiplication. We call that PE prime, proto Raghib prime. We modified it to get the classical Raghib, yeah, which has homomorphic addition, decryption correctness, and scalar multiplication. Yes, of course, because the scheme encrypts bits. So okay, good. So you can multiply by 0. Okay. Then the final variant is just a modulus reduced version of Raghib. Okay. Now it's time to put them together to get homomorphic multiplication. Shall we do it? Okay. All right. So let's. This is Vika. So let's do it. Okay. So I take 2 ciphertexts, an encryption of M and an encryption of M prime, and really one of these encryptions I'm going to think about it as the Raghib encryption, and the other one I'm going to think about it as a modulus reduced or scale invariant Raghib encryption. Okay. As we saw, we can go back and forth, so no problem. All right. Yeah. So this is mod Q and this is mod 1. All right. So we are actually working with 2 different groups. So just not to get confused with ourselves, or myself for that matter, I'm going to explicitly write it as the mod Q is plus Q times some integer. Yeah. This is plus some integer. And now the cipher, everything is over integers or rationals. This one. All right, so what do I want to do? I want to, from C and C prime, construct a ciphertext which decrypts in the sense of in a product with a secret key to an error plus the product of the messages times q over 2. So in other words, I want to come up with a reggae encryption of the product of the two messages. Yeah, makes sense? This is the goal. This is what I want. All right, how should we do it? And really, this was the bottleneck, for at least for us, for a long time, for a few months. We thought of homomorphic. How would you do homomorphic encryption? Okay, you want to add and multiply ciphertext. Yes. So it makes sense to work with an underlying object which supports both additions and multiplications. In other words, called a ring. Yeah. So without rings, how can you possibly do homomorphic encryption? That was a bottleneck that we were hitting against. In one morning, we realized that you can think a little out of the box, and you can actually multiply vectors in a vector space. You can think of a couple of different ways of doing it. It's not one morning. I mean, we tried a few different things. Yeah, so you can do it. And for those of you who haven't seen it, how would you multiply two vectors?
Tensor product.
Who said that? Oh, okay. All right. Very, very good. Okay, so then you should have written the paper. We tried like 5 different things and 2 different things. Okay, yeah, so you can tensor the two ciphertexts, yeah? The multiplying by 2 is just an annoyance. Never mind, yeah? You can tensor the two ciphertexts, and what happens, you just take the 2 left-hand sides of this equation and multiply them together. These are numbers, right? You multiply them together. Yeah, C times C in a product S times C prime in a product S is C tensor C prime in a product S tensor S prime. So what I'm really doing is multiplying the 2 left-hand sides of this equation and multiplying by 2, which for some mysterious reason I have to. Okay. Yeah, makes sense. All good. What do I get on the right-hand side? Well, I multiply the 2 right-hand sides, yes. And brace for it. Yeah. So some ugliness that comes into picture, and you trust me, or you can go back and verify, the recorded video. That this is really a small error. Right? Why? Because this, just to start with, this is an error that's E is a small error relative to Q, and E prime is a number that's smaller than 1. So it can only reduce the size of the error further. E is a small error, mod Q. M prime plus 2Z prime is a small number. Well, I want it to be a small number. And if it is a small number, it's a number of size poly n independent of Q, then you're good. Same thing here. And here is the key signal.
Wait. Why is this so small?
All right. Well, hold that thought for a second. Yeah. So, and then you get Q times the multiple, which I don't care about. It's small multiple, I don't care about it. Okay. So really, this guy is good. Mod Q. Really, it's Leo's question. How large is the error? Good. So the error length is proportional to the actual error length E, which is like eta Q, really. Just smaller than, I think of it as smaller than Q. This is also eta Q because I had an error in the torus multiplied by Q is small as well. Really, the question is how large are Z and Z prime? So what are Z and Z prime? I take a ciphertext, multiply it with the secret key. These are vectors in ZQ to the n, potentially, right? The coefficients is largest Q. Multiply them. How large can they get? Q squared. Yeah. So Z could be as large as Q. I'm dead, right? Not so. I said something prematurely here. And here's a beautiful theorem of Applebaum, Kash, Pikert, and Sahai, who show that LWE with small secrets, what does small mean? You choose the secret from the error distribution as well as the error. Yeah, so they're small. LWE is exactly as hard with small secrets as with random secrets. So we were somewhat stupid to begin with to use random secrets and so much entropy. That entropy didn't matter at all. I mean, you should really have used small secrets. Yeah. That's beautiful, because then what it tells us is that this Z, the length is proportional to the L1 norm of S. Therefore, the noise grows by L1 norm of S, which is small, which is poly n. Very nice. Yes? Beautiful. So, the pieces were there. Thank you. And at this point, we think of the ACPS theorem as I give it as an exercise in my class. But at that point, we were like, thank you. Saved us. Very good. Yeah. So this is that. And you need to round it because this doesn't live in Z mod QZ. It has sort of rational coefficients, but you round it, it doesn't matter. The rounding error, again, introduces an error proportional to the L1 norm of S tensor S, which again is small because S is okay, so what you get out of this is a ciphertext whose inner product with S, if you squint, okay, but something like S, is an error plus looks exactly like a regF ciphertext. In fact, this is a regF ciphertext relative to the private key S tensor S, not relative to S itself, which is what we wanted. Now, if you do it again, it'll be relative to S tensor, S tensor, S tensor, S, and then you die, basically.
Question. So, you don't actually need S to be small in the end, right?
You do. You actually do. For modulus reduction, which is what we did, you do need S to be small. Yeah. Very annoying. I know that Vika is very bothered by it. It doesn't matter in practice.
No, I know that it.
Yeah.
I know that
Yeah.
you have the equivalence and it's okay, but
Yeah.
it just seems a bit strange. I mean, you can't do like some bit decomposition.
Yeah, not here. And not that I know.
There are different ways to do it. In fact, I think it's in your paper. Depending on whether you do the two things at the same time, or you do, there's this key switching operation where you change both the modulus
Yes.
and the key,
Yes.
or if you do only one of the two, and then depending what combination you do, you can do slightly different things. One of these things does not require the key to be small. I forgot which.
Well, again, as I said, it's been 10 years. I forgot I reconstructed the whole thing from scratch, so it could have been, but
I cannot remember what, but perhaps you're thinking about the other one.
offline. Okay, it's a beautiful question. Offline, it's either resolved already in one of my papers, it turns out, or not. In which case, it's a good question.
I thought that the Brakersky 12 paper, like
Brakersky 12, I do think needs S to be small. I'm fairly sure, unless Brakersky can communicate back.
My question is a bit more meta. Why do you care so much that S has to be
That's
small?
my question. That's my question to.
I mean, you shouldn't need S to be small.
I agree with both of you. This is the way to make. Let me do my talk. I'm sorry.
So why do you combine the mod Q scheme and the mod 1 scheme? Why don't you use the mod 1?
Beautiful question. Mod 1 scheme, because you can. That's a short way. If you just use two mod Q schemes, the error blows up a lot, and that's wrong. If you use two mod 1 schemes, that's fine. Except later, in a minute, I'll want this ciphertext to actually be integer ciphertext.
Yeah, I think the two are equivalent.
Yeah, completely equivalent.
Both mod 1 and then raise it up.
Completely equivalent. Totally equivalent. Yeah. So again, I said I reconstructed this from scratch. Following actually, plug Daniele's talk from Eurocrypt last year, which again sort of reconstructs the GSW scheme from scratch. Very nice. And I said, well, should be able to do that for BV as well, right? Not as clearly, but by far. All right. So not happy with this because now the encryption scheme is a regF encryption scheme. It's a regF encryption of the product of the bits, but under a much larger key. Therefore, the ciphertext is a lot larger. I want to reduce the size of the ciphertext. So we call that dimension reduction in the BV paper. But really, this is a technique that you could use to switch an encryption of a message under any key to an encryption of S and enter any different key. They could be the same size. One could actually, you could be switching to a larger key. For what reason? I don't know, but you can using this technique. So, so Craig sort of presciently call it key switching. All right, so again, what do I want to do? This is what I want to do. I want to come up with a ciphertext which decrypted with S is an encryption of M times the same message under a shorter key. That's what I want to do. How do you do it? Okay. Now comes another fantastic property of the Ragheb encryption scheme, which is linearity. And so decryption, if you look at it, is a linear function of the secret key. So whatever is here, yeah, I mean, you have a linear function whose coefficients depend on the ciphertext. You apply that linear function to the secret key. What you get is a message. Not quite, but you get, and then you need to do some sort of a thresholding or rounding, but more or less it's a linear operation. That's beautiful. That's amazing, and that's really what we're going to use here. So what we're going to do is we're going to sort of change things a little bit. We are going to have a public evaluation key. So what is V? I have the secret key. I'm Alice. I have the secret key. I'm encrypting stuff to be computed on. I am also going to publish an evaluation key, which will help the cloud do this key switching operation. So poor thing, it cannot do it by itself. I'm going to actually help it out. Of course, I don't want to help it out too much. Yeah, helping it break. This is it. All right. So linearity of decryption. So what is decryption? Again, it's an inner product. What is an inner product? It's scalar multiplication with large coefficients potentially, because C has large coefficients, mod Q, and addition. So we do know a scheme which supports scalar multiplications and additions, which is what we called proto-Ragheb back in the days, back in the hours. That's what we do. So the evaluation key is a proto-Ragheb encryption of the new secret, the old secret key, the tensor, the one that we are going to switch from, under the key that you're going to switch to. Yeah. So this is what I'm going to publish this. Yes. So let's see if this actually helps. What this key does is it allows you to apply the linear function, which is C in a product S times S, right? The linear function. Take an encryption of S times S and multiply it with C in a product with C. And C in a product S tensor S is error plus MQ over 2. Yeah? Which really is the encryption of the Ragheb encryption of the message. You just did it. Does that make sense? Yes. So, okay, so you say, okay, you know what, Alice is going to publish this encryption of S tensor S with S. Okay, then you ask, is that actually an okay thing to do? Well, depending on who you ask. So this problem that, publishing an encryption of S tensor S under S is okay, is called the circular security problem. So we don't know the status. Maybe it's okay, maybe it's not. You can assume that it's okay and things work through. But it's a problem. So in reality, if you don't want to make these sort of funny assumptions, if you want to do everything from LWE and LWE only, you can't do this. What you do instead is you switch from S tensor S to a new secret key S prime. So rather, you encrypt S tensor S with a new secret key S prime. Right? That's okay. These two, what you're encrypting and what you're encrypting under are independent. So that's actually okay. Semantic security, CPA security guarantees that this is fine. And now you say, okay, fine. So that's what? You go from an encryption under S to an encryption under S prime. Now I want to do another multiplication. What do I go under? S double prime. And to do that, I need to publish an encryption of S prime tensor S prime under S double prime. So you need to really publish a chain of these evaluations. Okay. Then you can go. Well, and if I publish 100 length chain, I can evaluate depth 100 homomorphic, depth 100 circuits.
In this case, do you need public key or private key will be sufficient?
Private key is sufficient.
You have to encrypt E of M under S tensor S, right? Because it's not the same, like in order to perform it homomorphically, how do we do it?
So you can actually compute, you as in, you don't know the secret key, yeah? You can actually compute an encryption of a message under the secret key. The message itself is an encryption of the message under the secret key. Yeah? Does that make sense? It's not a secure encryption, but you don't care about security. I'm the one who cares about security. Yeah? So 0, comma MQ/2 is an encryption of the message. It's a regular encryption of the message under the secret key. This. All right, so good. So this is it. So the big picture, what does the encryption scheme consist of? It consists of an evaluation key, which is a sequence of private keys, so encrypted in this way. Yeah. Each time you evaluate a multiplication, you first do tensoring. You go to start from encryption under S to S tensor S. Then you use one level of the evaluation key to go to S prime. Then you multiply S prime tensor S prime. Then you go to S double prime. Keep going. That's good. So now, yeah.
Did you use tensoring for multiplication?
I did.
When you use multiplication again, which would need tensoring again?
Sorry, say again. Yeah.
You tensor in order to be able to do multiplication.
Yes.
But then the way to switch keys is use again multiplication.
No, it's in a product at the end of the day. So it does, you do at the end of this two-step process, get an encryption that looks exactly like before, in the sense if you start with an n-dimensional ciphertext, you get an n-dimensional ciphertext. Then you tensor, you grow, and then you shrink. Keep going. But the thing is, you can only keep going for, a pre-specified number of levels, and so this is called a, this is all we could get without circular security, so we called it a leveled homomorphic encryption. Yeah, this makes sense? Okay, so scheme has a ton of nice properties. First, it's a very easy thing to adapt whatever I did to the ring setting, to the ring LWE setting, completely trivial. An exercise in an undergraduate class, I would say, go that far. And in fact, you can also do modular LWE. This is what we did in BGV. We called this generalized LWE in BGV 12. It's really what's called modular LWE at this point. You do all these things very easily. And once you go to the ring setting, you can actually do sort of SIMD computations. In other words, you don't need to encrypt one bit, which is what we did. You can encrypt a sequence of bits or a sequence of numbers. And then you can sort of add a vector of numbers, and you can coordinate-wise add and multiply these things just in one shot. Okay, just fantastic, really. One shot, you get n operations. More than that, you can actually compute on packed ciphertext. It doesn't. So how does SIMD computation help? If you want to compute the same function on many in parallel on many inputs, that's where SIMD helps. Yeah, you do the same operation on the each element. What if you just have one input? Per person, I just have one input. And I want to compute on it, but I don't want to sort of look at, I don't want to encrypt each number separately. I want to encrypt all of them together, and I want to compute inside the ciphertext somehow. This again can be done. So it's fantastic sort of properties of the scheme. Not all in sort of the original works. Lots of works kind of actually built these properties. And this is Gentry, Halevi, and Smart. Okay, so yeah.
Something odd that happens when you move from LW to ring LW.
Yes.
Tensoring part, because tensoring for rings
Yeah.
is less.
When you multiply.
Not really. I think if you think about it as a module, right? Tensoring ring LW is like a two-dimensional modular operation. It works exactly the same way. You can take it offline. But
Tensoring, right?
sorry?
You don't need tensoring for rings.
No. But that's the thing. Ring LWE is not a. Even if you work with the ring LWE version of the scheme, you still need tensoring, because it's a.
Polynomial.
No. No, polynomial LWE, ring LWE, everything you need tensoring. Because the ciphertext are always two-dimensional vectors over the ring, if you use ring LWE. Then if you don't need tensoring. Offline, yes.
I would submit you don't need tensoring and LWE either, because all you're doing is multivariate polynomial multiplication.
Which in a sense, you go from, yeah, I mean, it is,
Well,
it's another way of looking at it. If you have a fundamentally different way of looking at it, yeah, go for it. I mean, I'd be very happy to get rid of the tensoring.
I mean, it's tensoring over a different ring.
Yeah.
That makes a difference.
Right. So here we are tensoring over Z, and there you would tensor over the RQ, basically. Unless you're working with ntrue, where things are different. I mean, ntrue is really the ring scheme. Like ring LWE is not a ring scheme. It's a module scheme. All right. So we can take this offline. How much time do I have? 7 minutes. Really? All right. Yeah.
I'm in front of you because you're also the organizer. So I was a bit puzzled with the schedule. There is a 1 hour break.
Okay, it's not a 1 hour break. You should read your emails. No, what I mean is the following. Let's get to it in 5 minutes. Okay.
You want to stop at 7.
Yes, I do. Oh, you are the session chair. Okay. It's like, why are you asking me these questions? Got it. Okay, so you know what? You can. I'm not going to tell you about the GSW scheme. Super nice. And the thing is, you go to YouTube, you have five different talks on GSW. So I'm not going to really add much to it. Okay. Yeah. Very, very nice game. Eigenvectors. And really, it's 2 slides. Okay. Compared to I don't know, what was it? 10 slides, 15 slides, something like that. So it's much more compactly described. Very nice encryption scheme. And let's sort of compare quickly, right? So it turns out that BGV and BV and Brokersky and so forth, we admit shorter ciphertexts. In other words, you encrypt a message into a vector in the primitive version of the scheme, or if you use the ring LWE, you encrypt a vector into a vector. Yeah. So the packing constant is the plain text to ciphertext ratio is some constant. GSW doesn't. Well, I haven't told you what GSW is, but it encrypts a vector into a matrix. And then you do what? It actually does worse. I mean, you can solve these sort of short ciphertext problems asymptotically with hybrid encryption. So you never encrypt the message, you encrypt a AES key, and then but doesn't. Still hurts.
What's IRL?
In real life. Oh, am I that old or that new? I don't know. It's a good. It's a kosher thing, right? Oh, good. Yeah. Someone who looks decidedly younger than me says yes. All right. So GSW, it has, okay, so that's one sort of disadvantage, if you could call it, of GSW, and the reason why GSW is not like used all over the place, just plain, that's it, people still use BGV, yeah, at this point. But GSW has tons of other nice properties. Turns out it has slower noise growth, doesn't matter what it is, but really the important property of GSW is that it's a very expressive scheme. You can start from GSW and do not just fully homomorphic encryption, but fully homomorphic signatures, attribute-based encryption, predicate encryption, Everything that you're going to see today, later, is essentially going to build on GSW. Yeah, that's about right. Very, very nice game. So really, it is still open how to come up with the best of both worlds scheme. People have sort of done that in some senses, but to the best of my knowledge, there's no fully satisfactory solution.
So you want GSW with shorter ciphertext?
Yeah, GSW that encrypts vector into a vector, never makes it into a matrix. It's not quite the case.
In the ring setting, it is quite close to a vector.
Log Q factor away, yeah. Instead of a log Q vector, length vector, that's what you would get from BV. I think it's a log Q by log Q matrix. It's still away. Still a factor of log Q away. It's not n log Q away, but it's log Q.
No, but that's one of the improvements of the CFHE paper. They transform the matrix into a vector. No?
No, you can't. No.
Really transforming a matrix into a vector.
It's
like
just taking
mix
one
them
row of
together.
it.
Using them both at the same time.
Yeah.
But
Inside the computation, you still have the. Inside the computation, there's still the matrix. But then you can compress it to a vector. Then you make it a matrix. You compress it to a vector. Yes, that's.
No, it's more like
External.
yeah, no.
One has to be a matrix and the other has to be a vector to make the product.
Possibly. Yeah, is that right? Okay, speak.
Exactly. You cannot. You are not forced to do
Yes.
matrix
Yes.
vector.
Yes, exactly.
But you are not eliminating completely.
Right. Exactly. That's good.
Yes, still, I just wanted to understand the open problem you're offering.
Open problem. This is the open problem. Yeah. So really, like, do BV, except nicely. Okay. So it turns out. So all we did was sort of homomorphic encryption, leveled homomorphic encryption. So you can go a little bit far, but not really completely. And there's this beautiful theorem. I'm just going to state it. The proof is 2 slides long, but I don't have 2 slides time. What you can do, this is from Craig's original work. It's a beautiful theorem. It says that if you have a homomorphic encryption, that can, rather, let me put it this way. If your decryption algorithm is simple, it can be evaluated in a small multiplicative depth, let's say D, and your homomorphic encryption is just powerful enough to evaluate the decryption circuit, D+1 depth if you want, then you get really fully homomorphic encryption, meaning I can fix the parameters of the scheme, encrypt a message using these parameters, and you can later decide you want to compute a 1,000,000 depth circuit, in theory. You can do it. That's fantastic. One more thing about the going from leveled to fully, you actually need, we worked hard to sort of say, you don't need, you want to do everything from LWE, but the only way we know to get fully homomorphic encryption is making the circular security assumption, which roughly says publishing an encryption of the secret key under the secret key is okay. Is it okay? Is it okay under LWE? That's really what I would like to prove, but we don't know at this point. Okay, so nice slides, I think, but yeah. All right, so the open problem is either prove that BV or GSW, one of these schemes, is in fact circular secure. You can actually encrypt the secret key under the secret key, and it's okay, it's secure under LWE. And really, it turns out you don't have to think about 2 different problems. It turns out they're the same problem. The circular security assumption you need for both schemes is the same. It's not surprising to me, but that turns out that's the case. Or just completely eliminate this whole bootstrapping methodology, just find a completely different way to directly do FHE under LWE.
Is it high-level ID, or is it provable that
This is provable, yeah. This is just writing it down,
that they're equivalent?
Yes. Just write it down. So
Okay.
we can write it down offline. Okay, so yeah, it's not surprising actually. It turns out. Many other things you can do. You can do multi-key FHE. You can compute on encryptions under different keys, whatever that means. Lots of implementations. It's not even complete. There's things here which you can't see. Okay. Standardization. All right, so let me leave you with 3 questions. One, like 2 of them I already told you about. Best of all schemes, HV and GSW together. Why circular security? I really don't know. I'm very conflicted about this. On the one hand, there are sort of recent results. Rishabh, where is Rishabh? Goyal, Kopula, and Waters, Venkata must be here too, and Waters, they showed an example of an encryption scheme which is secure, CPS secure, but not circular secure. Okay. It's a somewhat contrived scheme, but it's actually an LWE-based scheme. So I'm saying, why is it not regev? Okay, so now I'm starting to get a little antsy. Okay. Yeah, I'm a little. And before I was like, of course regev is circular secure, but now not so sure. So that's one thing. So it would be nice to prove that LWE regev is circular secure. It turns out that there's a completely different way to get pure FHE from this thing called indistinguishability obfuscation, which does not refer to circular security at all. So there is a way to bypass circular security, except you replace it with a huge hammer. Okay, now that gives me there's some indication. Okay? This is a work with Ron, Rachel, Stefano. Finally, this is a philosophical question. Okay, the only way we know to do leveled FHE or FHE is with lattices. Somewhat antithetical to the point of this whole program, let me ask: do we need lattices in the first place? There are proposals. There is a very nice framework of Koji Nuida, and Craig gave talks about it, but I don't think it's ever been written down, using sort of non-commutative group actions to get fully homomorphic encryption. It's a framework. It's never been instantiated securely as far as I know. It's a very nice, if you really want to do something completely different. If you want to come to the lattice program and and eliminate the need for lattices, maybe that's a place to look at. Yeah. So that's yeah.
Your second one, does I/O imply secure encryption generically?
I don't think that it seems possible you can do it, but there's no exact. I don't think there's a paper that actually.
Yeah, I don't know. That's a good question. But then my argument would be.
Yeah, my point is yes, it's like FHE.
So I/O actually implies the existence of an encryption, right? Correct me if I'm wrong, which is secure but not circular secure. The other way around. But maybe I/O implies circular secure encryption as well. I'm not sure. I'm not sure. Okay. All right. So this is really all I want to say. Both Daniele and I maintain sort of a page with tons of links related to sort of work on FHE, and update it when we have nothing better to do. I update it when I have nothing better to do.
How often is that?
Very often. When you have a kid, it's you end up with lots of free time. Right. So that's that. I'll take questions, but. Alice.
Your slides on the website. I noticed that the videos are going on the website, but not the slides.
Yeah, I'm happy to do it. Yeah.
So I asked this question, so they are collecting the slides and they will put them up after the workshop is over.
Okay, good. So
At the very end, because these slides
Thank you.
they get changed till the very so
That's
not next week, but they will be all there.
that's an even better solution. Yeah.
Maybe I misheard, but you seem to have said that Q doesn't matter for LWE, but doesn't the self-reduction from LWE dimension n to LWE dimension n over 2 and Q squared imply the opposite?
That actually implies what I said, right? You can switch from Q to.
But in half the dimension. So you square the size of Q, and you get n over 2 in the dimension. So the hardness is preserved, exactly. But that means if I take the same dimension and just increase Q, keep alpha the same, I have a harder instance.
Yeah, but he lives in a world where n bits and 2n bits of security are the same.
Yeah. I think that's maybe because this going from one modulus to another modulus, it does add error to the scheme, which is polynomial in the security. So
No, the hardness is the same, but it means for the same dimension, a larger Q it gives and the same alpha gives you a harder instance.
What you can do is you can go from a larger modulus to a smaller modulus with modulus reduction. It doesn't go the opposite way. In fact, Chris does go the BLPRS does go the opposite way, which
So it's not just n, what I'm saying is
Good
not
question.
just n and alpha that determines hardness. Q also matters.
I see. So you're saying n log q.
Correct.
Yeah, you're right. Absolutely right. One direction, maybe, I would still like to convince you that I'm right, but going down. But yeah, you're right. You can go from n dimension q modulus to n dimension q prime smaller than q modulus without any loss. Small loss in error. Thanks. Yeah.
So what about CCA1 security? What is the status of
The status is pretty terrible. We can actually do it from, I think Nigel and friends had a work that showed how to do it from the lattice knowledge of, I know what to call it, exponent, for lack of better words, assumption. And we have a work with Ran and Silas and Srini that does it from I/O. But that's not the right, so it's completely, it's completely open. No, not completely open. So there are nuances to what I'm saying. Tell you offline.
Maybe it's worth mentioning, there's a lot of quantum people here. I think the knowledge assumption that is made in that paper is quantumly broken, no?
I have no idea what it is to begin with, so...
it's basically the assumption that if you can produce a BDD instance, you know the answer of it. And quantumly, that's...
No, I'm not sure. I'm not sure.
What's the total of this?
That's a very interesting question.
Oh, I see. You're saying just to prepare a superposition measure. That's it. You're not doing anything fancy. Happy? Right. So then now let me get to Damien's older question. I want to sort of meet with sort of the Lattice program participants. A bunch of people are welcome to join. To sort of decide on what we are doing for the semester, which I know is research, but we'd like to kind of do sort of joint activities. One of the things is, this is not being recorded, right? One of the things is a seminar on lattices, which Noah and Rishabh are already organizing, and they'll be in touch with sort of all of you to sort of get ideas for talks, you know. But we also want to do potentially other things. I've talked to some of you personally, sort of one-on-one, and you have suggested ideas, but I want to sort of get a collective sort of input as to what, if anything you would like to do together, collaboratively, in a structured way. Okay, so we'll meet 116, which is, you know, right next to Martina's office now for half an hour. Feel free to sort of take 5 minutes to get coffee